I used to remember this as metabolic acidosis 1.2, metabolic alkalosis 0.7. Okay, that's the way you need to remember also, because it's 1.2 is a correction factor there. Okay, so metabolic acidosis 1.2. The secondary response to metabolic acidosis, what is meant by metabolic acidosis? Metabolic means bicarbonate. Acidosis means decrease in bicarbonate. So when there's a decrease in bicarbonate, I'm speaking about metabolic acidosis. When there's a decrease in bicarbonate, the secondary response is going to be increase in the minute ventilation, so that the CO2 also comes down, right? So this response appears in 30 to 120 minutes and can take 12 to 24 hours to complete. The magnitude of the response is defined by the equation that delta CO2 is equal to 1.2 times delta bicarbonate. Okay, so I'm saying you that in a patient the bicarbonate has dropped around 10, it has dropped from 24, it has come to 14, right? So 10 is a drop. So what is the expected carbon dioxide? Okay, so the bicarbonate is 14. The bicarbonate is 14. Okay, it has dropped from 24 to it has dropped up to 14, means 10 drop. So 10 into 1.2 is 12, right? So what is normal PaCO2? It is 40. 40 minus 12 is going to be 28. Okay. So using a normal PCO2 of 40 mmHg or a normal bicarbonate of 24, the expected PCO2 is equal to 40 minus 1.2 into 24 minus current bicarbonate. Okay. For example, in a metabolic acidosis, the plasma bicarbonate of 14, which we just did, 24 minus 14 is 10. Okay. So my patient has a metabolic acidosis and the bicarbonate is 14 there. So what should I do? What is the delta bicarb? How much it has changed? It has changed from 24, it has dropped to 14. So the change is 10. Okay. So what is the correction factor? Correction factor to find out what is the expected PCO2 is 1.2, right? So 1.2 into 10 is 12. So 12 should be the change of carbon dioxide. So what is the expected carbon dioxide? From 40, it has to change to 12. Okay, so that's 28. Okay, 12 has to be subtracted. So 28 mmHg. Okay, so if your patient is suffering from a metabolic acidosis with a bicarbonate of 14, then the compensatory mechanism, the PCO2 should drop down to 28, right? If it has dropped down more further, instead of 28, it's only 20, meaning there is super added respiratory alkalosis. Okay, but instead of coming 28, if it's starting at 38 or 40, which is pretty high, then it means that along with your metabolic acidosis, there's respiratory acidosis as well. This is how you need to interfere these things. If the PCO2 is more than 28, there is a secondary respiratory acidosis. If the PCO2 is less than 28, there is secondary respiratory alkalosis. Okay, so given the bicarbonate, you should know what is the expected PCO2, and if the patient's PCO2 is more, then there is superadded respiratory acidosis. If the expected PCO2 is less, patient's PCO2 is less than the expected, then there is secondary respiratory alkalosis. This is how you need to interpret. Okay, so now coming to the metabolic alkalosis 0.7. Okay, the secondary response to metabolic alkalosis is a decrease in minute ventilation and subsequent increase in PCO2. What is metabolic alkalosis? What does metabolic mean? Metabolic mean bicarbonate. Alkalosis mean increase in bicarbonate. Whatever happens to one parameter, the same thing should happen to the other parameter, right? If the bicarbonate increase, PCO2 will increase. When the bicarbonate decrease, PCO2 will decrease, right? So metabolic alkalosis means bicarbonate increase. So when the bicarbonate is increasing, compensatively the CO2 also should increase. Okay, for CO2 should increase, what should happen? The minute ventilation has to come down, respiration has to come down, right? But I already told you that decreasing this kind of respiratory parameter is actually a blunt response. Okay, so this particular response of blunting the respiration or decreasing the minute ventilation is not as rigorous as a response to metabolic acidosis, because the peripheral chemoreceptors are easier to stimulate than to inhibit. Okay, so I told you the metabolic acidosis is 1.2, metabolic alkalosis is 0.7, the correction factor is 0.7. The magnitude of response to metabolic alkalosis is the delta PaCO2, the change in CO2 is 0.7 times the bicarbonate. So when I give you a metabolic scenario, okay, I'll tell you what is a bicarbonate. You have to tell me what is the expected PCO2. Okay, now in metabolic alkalosis, the correction factor is 0.7. In metabolic acidosis, correction factor is 1.2. Okay, so using a normal PaCO2 of 40 and normal bicarb of 24, expected PCO2 can be written as 40 plus 0.7 into current bicarbonate minus 24. You need not go into this kind of looking complicated equations. You can just check out what is the correction factor, apply it. Okay, so for a metabolic alkalosis with a plasma bicarbonate of 40, now you tell me. So what is a normal bicarbonate? It is 24. Normal bicarb is 24, right? This is normal bicarbonate. How much has it increased? From 24, it has increased to 40, right? So how much is the increase? How much is the delta? It is 16. 16 is the delta bicarbonate. So delta bicarbonate is 16, right? So what is the expected change in PCO2? What is the correction factor? 0.7. So 0.7 into 16. Okay. So this will be the change in PCO2. Okay. So bicarbonate, we have 16, PCO2 is 0.7 into 16 is 11. So expected PCO2 is 40 plus 7 is 51. Okay. So if the patient's PCO2 is more than 51, then the patient is suffering from a superadded respiratory acidosis. Okay. If it is less than 51, then the patient is having superadded respiratory alkalosis. Okay. So this kind of things is only borderline, because I told you that metabolic alkalosis has very blunt compensatory mechanism in the lungs.